this exercise follows up from the previous exercise. So in exercise 1 in the previous video, we computed the correlation matrix ourselves using linear algebra equations. Here in exercise 2, we are going to use numpy's function numpy.coreCoef to compute the correlation matrix for us. So we are not going to input the covariance matrix. That's what coreCoef will compute. Instead, we just directly import the data matrix, and we don't need to do anything fancy. We don't need to mean center. We don't need to do any of this kind of normalization stuff. numpy.coreCoef will do that for us. And, obviously in the future on your data, you'd want to use numpy.coreCoef, but I think it's really important and useful and handy to understand the math behind what numpy.coreCoef is implementing. And that's why we went through all this manual computation on our own. Okay, so here, this is just a bit of a visual confirmation that we are doing the right thing. We compare the correlation matrix that we computed in the previous exercise with numpy's correlation matrix here, and then they should be there should be no difference between them. Of course, there's going to be little computer rounding errors here and there, but you can see certainly at this scale, at this level of precision, it's just a gray box. It's pretty boring, actually. Okay, so after doing all of that, we are then going to inspect the source code of numpy.coreCoef, and we're going to see whether NumPy computes the correlation matrix in exactly the same way that we did in the previous exercise. It turns out the answer is no. It's a slightly different implementation using an operation called broadcasting, but we'll get to that. I'll show you in the code. It's essentially the same concept. One thing you have to be mindful of when using the coreCoef function is that the data are in the proper orientation. So if the data are not oriented, if the matrix is not oriented as observations by features, then you're actually going to get the incorrect result. And that correlation matrix is actually 2000 by 2000, which is the wrong shape. So this is the wrong size. This is still a valid correlation matrix, but this is the correlation within observations, not the correlation across features. So that you see here, it's just the wrong size. Okay, so it's maybe a little bit counterintuitive, but if you store your data as observations by features, then you actually need to transpose the data when you're using numpy.coreCoef. Fortunately, it's actually really easy to determine if you're doing it the right way, because the correlation matrix should be features by features, not observations by observations. So if you're computing a correlation matrix, you can check the size or visualize it like this. If the size of the correlation matrix translates to or corresponds to observations by observations, then no problem. You just need to transpose the data matrix. Okay, so let's see. So now we get, here you can see, this is the correlation matrix from NumPy. So here I'm visualizing cormat. That's what we computed in the previous exercise, cormat that underscore NumPy, and the difference between them. And of course, we expect that to be 0, certainly within computer precision error. Okay, very nice. Now we can look up this, the source code for this correlation function. So question mark, and then numpy.coreCoef. And that will open up this little window to the side. So we can see the doc string. This tells us in LaTeX code a bit about the math. So here you can see it's C divided by square root of CII times CJJ. So this is the covariance between I and J. And this is the product of the variances. And then we take the square root here. Okay, so what I want to show you is the code down here. Inside the NumPy source code for the correlation coefficient is generating this matrix C, which is the covariance between X and Y. And then we get the diagonal of C to get the diagonal elements, which are the variances create this variable here, standard deviation, which is the square root of the diagonal elements, so the square root of the variances. And then we do 2 lines of division, or I should say numpy implements 2 lines of division. This is dividing by a column vector, and this is dividing by a row vector with exactly the same variable here. Now, this is an operation called broadcasting or division broadcasting. This is not a operation in linear algebra. This is not an operation you would find in a traditional linear algebra book. It's a little bit more computationally efficient, which is why NumPy implements it this way. The reason why I implemented it using matrices the way I did in the previous video is because that is closer to the math. So I want you to see the relationship between the math, the equations, the theory, and the code. And then in practice, it's fine to use more numerically stable approaches of the linear algebra operations. Okay, then last thing here is to also check out the source code for the cove function. I didn't actually make this part of the exercise, but we can still scroll down and look at, I think it's really interesting to see the source code for all of these operations now that you understand the math. Go through this book, you understand the math, you understand the logic and the theory, and then you can just open up all of this code and see how the NumPy developers actually implemented these operations. Okay, so I had to scroll down here to the bottom. Here is the key point. So the covariance here is the dot product or the dot function, which actually implements matrix multiplication between X and X transpose, where X is the data matrix that has been mean centered. So all of the columns have a mean of 0. That's what this line does. Now there's some extra stuff in here. This is also implementing broadcasting subtraction. There's conjugates and so on, just in case there's complex numbers in the matrix. So there's more going on here, and that's because this NumPy function needs to be able to handle different situations, different kinds of variables, different kinds of data, and so on. But I want you to see that everything that you are learning in this book is being implemented in NumPy. Sometimes, it might seem a little bit more involved, but I believe that you will now understand a lot of these linear algebra operations.